Now that we've introduced series and parallel circuits, let's look at how the current behaves at the nodes and branches of these circuits. So we know that for a series circuit, the current is the same everywhere because there's only one path, there's only one loop. But in a parallel circuit, the current can take parallel paths. So let's take a look at a parallel circuit. If we have a source voltage here, and suppose we just have two resistors in parallel like this. And I'll let this be R1, I'll let this be R2, and we'll call this Vs. Okay, so at our source, power source right here, there's going to be a current, Is, that's generated, and the amount that's generated depends on the equivalent resistance that the voltage source sees. Let's just call that Is for now. Now Is is going to flow into this node, and unlike a series circuit where it would just continue on one loop, the current has two choices it can make. So either it can come down this branch and go through R1, or it can go down this branch and go through R2. And then once the current kind of splits, this current that takes the R2 path is going to come back around here. They kind of reconvene at this node here, they recombine, and then it comes back and returns to the voltage source. But here's the thing, the current that comes into this node and splits down this branch and this branch, we don't lose any current. So basically all the current that comes here is either going to take this branch or that branch. So we know that Is, it's generated by the source, is going to be equal to the sum of I1 plus I2 if I1 is the current that takes this branch and I2 is the current that takes that branch. And this is at this first node right here. Down here at this bottom node, so if I label this node A and I label this node B, then here's the situation at node A. The situation at node B is we have I1 coming in, I2 coming in, and then out comes Is again. So this is just I1 plus I2 is equal to Is. More generally, we can say, the way I would describe this is I would say the sum of currents going into a node is equal to the sum of currents going out of the node. Okay, and this is the definition of Kirchoff's current law. This is KCL, Kirchoff's current law. Okay, so let me show you an illustrative example. So suppose we have a circuit that looks like this. We've got a voltage source here, we've got a resistor, and then after that resistor, we've got a network of two parallel resistors, and then out of here, we've got another resistor. Here's one there, here. This can be a parallel branch. Let's put another resistor here, and let's label these nodes. So this first node, right, so the first location where the current could potentially split, I'll call that A. This next node, I'll call that B. And then we have another node down here. We can call this node C. Okay, now I'm going to label currents. Let's just call this current that comes out of here I1. This can be I2. This will be I3. We'll let this be I4. This will be I5. I5 also goes through this resistor, and then we'll let this current be I6. Okay, so by KCL tells us that we have that at node A, I1 goes in, and I2 and I3 come out of node A. So that means I1 is equal to I2 plus I3. Great, so then at node B, we have I2 and I3 coming in. So that has to be equal to I4 plus I5, which is the currents that are coming out. So this equation would be I2 plus I3 is equal to I4 plus I5. And then at node C, we have I4 coming in and I5 coming in, and we have I6 coming out. So this equation would be I4 plus I5 is equal to I6. And it's a good idea whenever we are solving circuits to just write out all the currents that are taking all the different branches and label the nodes, and then it'll be easier for us to use KCL and KVL to do circuit analysis.